Hey everyone, we're going to talk about section 4.1 today. This is on exponential functions. This is an introduction to exponential functions. Um, so, first off, let's go ahead and look at an example of something that we're going to try to solve later on in this section. India is the second most populous country in the world, with a population in 2008 of about 1.14 billion people. The population is growing by about 1.34% each year. We might ask if we can find a formula to model the population P as a function of time T in years after 2008, if the population continues to grow at this rate. Now, recall that linear growth is where we have a constant rate of change. For example, linear growth would be something like f of x equals 3x plus 4. The slope of this equation tells us that the output increases by 3 each time the input increases by 1. In contrast, exponential growth is going to be about percentage rates of change. So if I compare these two ideas, let me make this text a little bit larger. Let's compare the growth of two different companies. Company A has 100 stores and expands by opening 50 new stores a year. Company B has 100 stores and expands by increasing the number of stores by 50% of their total each year. Let's look at a few years of growth for both of these companies. As we see here, both companies start with 100 stores. Then, Company A expands by opening 50 new stores a year. So in year 1, Company A has 100 plus 50, which is 150 new stores. In year 2, they have 150 plus 50, which is 200 stores. And in year 3, they have 200 plus 50, which is 250 stores. Now for Company B has 100 plus 50%, that's as a decimal, that's 0.5, times 100. 0.5 times 100 is 50, so in year 1, they also have 150 stores. In year 2, they have 150 plus 0.5, that's 50%, times 150. This is going to be 225 stores. And then in year 3, maybe I need to zoom in just a little bit here. In year 3, they're going to have 225 plus 0.5 times 225. This gives me 337.5. And depending on the context, we might round this up or down. So in year 1, both grow by 50, right? In year 2, store A grows by 50, store B grows by 75. And in year 3 here, again, store A increases by 50 stores. Store B increases by 112.5. So, notice that with this percentage growth in company B, that as the company grows larger, the number of stores added each year grows larger as well. So if we look at the first year we found by calculating 100 plus 0.5 times 100. Or if I factor a 100 out of this, then this becomes 100 times 1 plus 0.5. And this is equal to 150. This was year 1. For year 2, I had 150 plus 0.5 times 150. And similarly, I could factor 150 out of this. This becomes 150 times 1 plus 0.5. And remember, I said that 150 is equal to 100 times 1 plus 0.5. So we're going to rewrite this as 100 times 1 plus 0.5 times 1 plus 0.5. And the red there, the red section here is equal to 150. And this is equal to 225. And notice that this can be simplified as 100 times 1 plus 0.5 squared. And this is 225. Then, for year 3, we have 225 plus 0.5 times 225. Again, I can factor 225 out of everything. 225 is 100 times 1 plus 0.5 squared. And this leaves me with 100 times 1 plus 0.5 cubed equals 337.5. Notice a pattern here, right? Every year, this exponent increases by 1. So this brings us to the general form of an exponential function here. An exponential growth or decay function is a function that grows or shrinks at a constant percent growth rate. The equation can be written in the form f of x equals a times 1 plus r to the x power, or f of x equals a times b to the x power, where b is equal to 1 plus r. And here, a is the initial or starting value of the function, r is the percent growth or decay rate written as a decimal. Very important. We have to make sure that we write these percentages as decimals. And b is the growth factor or growth multiplier. Since powers of negative numbers behave strangely, we limit this b to only positive values. So let's look at an example. Let's write an exponential function for India's population and use it to predict the population in 2020. So at the beginning of the chapter, we looked at this problem. So let's see. India is the second most populous country in the world with a population in 2008 of about 1.14 billion people. The population is growing by about 1.34% each year. We might ask if we can find a formula to model the population P as a function of time t in years after 2008 if the population continues to grow at this rate. Okay, so our initial value here in 2008 is 1.14 billion people. So A is going to be 1.14 billion, or in our case, let's leave this as 1.14, and we'll know that our answer is going to be in terms of billions, okay? Our answer will be in terms of billions. So we'll do the calculation with just this 1.14 number. That way we don't have to type a bunch of zeros into our calculator. We also have this growth rate, right? This growth rate is 1.34%. Or as a decimal, this growth rate is 1.34 over 100, right? Percent means per 100. And this is the same as moving the decimal to the left twice. And this is this percentage as a decimal. Now, if I put all of this together, my function was in the form of a times 1 plus r to the x power. So this is f of x equals 1.14 times 1 plus 0.0134 to the this wants this in terms of t, right? F of t is equal to this, and our variable here is t. Now, if we want to use this to predict the population in 2020, 2020 is 12 years after 2008. Remember, t is in years after 2008. So all I do is find f of 12. And if I plug this into my calculator, I get about 1.337 billion people in 2020. And this is actually pretty close. This is a pretty accurate estimation. Let's look at some more examples here. A certificate of deposit is a type of savings account offered by banks, typically offering a higher interest rate in return for a fixed length of time that you'll leave your money invested. If a bank offers a 24-month CD with an annual interest rate of 1.2%, compounded monthly, how much will a $1,000 investment grow to over those 24 months? Okay, so we have a few bits of information here. We have a $1,000 investment, so I know that my initial value is 1,000. I also have some amount of time here, right? And I have a rate. I have a growth rate. But notice this is an annual interest rate, and it's being compounded monthly. Because this is an annual interest rate and it's being compounded monthly, I want to find a monthly interest rate here. So my monthly interest rate is going to be 1.2% divided by 12, which is 0.1%. This is the rate of interest that this earns every month. And 0.1% as a decimal is 0.1 divided by 100. This is 0.001. So if I write this exponential function, it would be in the form of f of m for money, or maybe a month rather, right? This is a function of the number of months, is equal to what? 1,000, this is our initial investment, times 1 plus 0.001 to the m power. And if I want to find out how much my investment is worth after 24 months, all I do is plug 24 into this. So this is f of 24, which is 1,000 times 1 plus 0.001 to the 24th power. And plugging this into a calculator, we get about $1,024.28. All right, let's look at some more examples. We have example 3 here. This is a nice chemistry example. Bismuth 210 is an isotope that radioactively decays by about 13% each day, meaning that 13% of the remaining bismuth 210 transforms into another atom, polonium 210 in this case, each day. If you begin with 100 milligrams of bismuth 210, how much remains after 1 week? Notice here that our initial quantity is 100 milligrams, right? This is 100 milligrams. Our growth rate, R, well, this is decaying, right? So our growth rate is going to be negative. This is going to be negative 13% because of this word decay that I see here. Negative 13% as a decimal, this is going to be negative 0.13. So if I created a function f of d for days, this would be 100 times 1, I could say plus negative 0.13 if we're more comfortable with that. Or I could just write minus 0.13 to the d power, which means that after 1 week, that's 7 days. I just plug in 7 here. And I plug this into a calculator. And I get 37.73 milligrams remaining. Next up. T of Q represents the total number of Android smartphone contracts in thousands held by a certain Verizon store region, measured quarterly since January 1st, 2016. Interpret all the parts of the equation. T of 2 is equal to 86 times 1.64 squared equals 231.3056. So interpreting this, I know that 86 is my initial value, right? 86 is my initial value. And what this means is that on January 1st, 2016, this region had 86,000 Android smartphone contracts. Let's see. My growth rate here, let's see. This is B, which is 1 plus R, right? Which in this case is 1.64. This gives me that R is 0.64. This means that the number of smartphone contracts increases let me write this down. The number of Android smartphone contracts, right? Increases by 64% quarterly. And this T of 2 equals 231.3056 means, so this part is the only part that we haven't yet explained. This means that at the end of the second quarter, there were approximately 231,305.6, or we'll say 306, Android smartphone contracts in this region. Okay, and I'll split the recording here.